Welcome everyone to the afternoon session. I would like to ask Anantakrishna to introduce the speaker for this session.
Very good afternoon, everyone. The second speaker for our University Symposium and the first speaker for the afternoon session is Dr. Viji Thomas from the School of Mathematics at IISER Thiruvananthapuram. Dr. Viji had joined the institute in 2013 and is the current head of the department at the School of Mathematics. Dr. Viji is an algebraist working in the fields of group theory, homological algebra, and commutative algebra. Although starting his career as an engineering major, he completed his PhD from SUNY Binghamton under Professor Kape and was a postdoctoral fellow at TFR Bombay. So he always has interesting and motivational stories to tell us about. He's very much enthusiastic about the club and mathematics amongst the students in general, and has always encouraged us to carry on. Today he'll be speaking on the maximal implies prime principle, which will involve primality of commutative rings. And without further ado, over to him.
Thank you. I want to thank the Math Club for giving me this chance to speak in their second foundation anniversary. So my talk will involve basically commutative rings with unit. You should know just what a commutative ring is and what is a prime ideal. I think this much most people would know. And from there, I will continue. So before I start, I think everybody knows that a maximal ideal implies prime. Then you would wonder, then what is this principle? We already know that a maximal ideal implies prime, but that is not what I'm going to talk about, obviously. So there is a principle, and the idea, see, initially I was planning because I was told that the audience is very broad, first years are also there. Then I was going to talk about the Basel problem, the sum of the squares of reciprocals of integers is equal to pi squared by 6 using some multivariable calculus. Maybe that would have been more better, but then I don't know how much you will learn or that can be used in future. So this, I believe, hopefully you will be able to use, some of the people will be able to use in the future to expect certain things. So it's a principle and usually not there in this Atiyah McDonald, Matsumura, Eisenberg, etc. The principle is not mentioned clearly, so I think it is beneficial. Okay, let me share my screen. Okay, so without any delay, let me tell you what I mean by this principle. So for that, I'll put up a few theorems. By reading those theorems, you will come to know what I mean by this. At the moment, don't worry if you don't know what is a MCS, multiplicatively closed set. Okay, so let me put up some theorems. Some will be known to you, and this should be known to you, most of you, those who have taken, let's say, commutative algebra. So let S be a multiplicatively closed set in a ring R, and let I be an ideal in R, maximal with respect to exclusion of S. Then I is a prime ideal. Okay. If you don't know what S multiplicatively closed set is, at the moment, don't worry, because I am not going to finally focus on this theorem. But I want to explain what I mean by maximal implies prime principle. So this is one. See, I is an ideal maximal with respect to something. Then it is prime. Now this is a theorem of Herstein. Let R be a ring and M be an R module. Let I be an ideal in R that is maximal among annihilators of non-zero elements of M, then I is a prime ideal. Again, if you do not know what is a module, what are annihilators, again, forget it. Don't worry about it. I will not focus on this theorem either. But again, what I want to point out here is, see, I is an ideal maximal with some property. Then it again appears to be prime. Cohen. Let I be an ideal in R. Suppose I is not finitely generated and is maximal among all ideals in R that are not finitely generated. Then I is a prime ideal. This is a theorem I will focus and I will sketch the proof because it has some corollaries, and that is why I'll focus on this. And this is more or less understandable, I think. And it has not too many words which you won't perhaps not know. Okay. Going ahead, Martin-Isaacs. Let I be an ideal in R, maximal among non-principal ideals, then I is a prime ideal. So again, the theme is I is an ideal maximal with some property, then somehow magically it happens to be a prime ideal. Let I be an ideal in R, maximal among ideals that are not countably generated, then I is a prime ideal. let I be an ideal in an integral domain are maximal among all non-invertible ideals. Then I is a prime ideal. Now again, those who don't know what is non-invertible or invertible ideals, don't worry, maybe we can discuss at the end. But again, I'm not focusing on that theorem. So theorems are listed only to show that see how maximal with some property or not having some property ends up being prime. That is my theme today. An ideal maximal with respect to containing only zero divisors is a prime ideal. Okay, so I hope I have kind of given the idea what I mean by maximal implies prime principle. So let me tell the story how I got to this. So over the years, not all at the same time. So during my PhD time and master's time, I had proved 2 or 3 as exercises from the first slide. Then during my, I think, postdoc also, I proved a couple. So they all were not proved at the same time, at different times. So at some point I started wondering, I think I remember proving something earlier also. Maybe there is something that we can do, like a principle, a proof that works for all of them, not different. And all those proofs, when I analyzed it, it looked almost similar. The proofs go similar. So I thought maybe there is more to be discovered. So I wanted to start around 2011 on this, but I started looking what other theorems are of that time. When I looked, I saw already a theorem by, I will show the reference at the end, that somebody had very recently, then, 2008 published something like this, which captures all of this and includes something more, which is, and I have taken this, the last one, an ideal maximal with respect to containing only zero divisors from that paper. So that reference will be given to you at the end. So I stopped, meaning they have put it in a more general framework. I still do not like that framework as much. I think you can put it in a more better, perhaps. And maybe you can think about it and maybe you can discover more. Now, before I go into any of the proofs, the Cohen's theorems proof is what I will focus on. Isaac's also we can focus on, but Cohen I will do. And what I want to say here is, if you somehow fell asleep at this point, or your parents or grandparents called you for some chore and you're gone, only thing I want you to know at this point is, see, somehow if in future you encounter an ideal maximal with respect to a property, then it is not a bad idea to expect that it is prime. Of course, you will have to prove that it is prime, but it is not a bad idea to expect. Sometimes in research, you have to expect things. And the reason I chose this is a theme that you can take home with this talk. So even if you have somehow fell asleep now, this is the theme that I want to focus on. Since it's a talk, I will at least give proof of one. And if you know the proof if you happen to be a person who knows the proof of the theorem I am presenting, I am sorry. I could have presented some other one, but anyway, I can't help with that. So I have chosen Cohen's theorem. And let me tell you why that theorem will. So this is the Cohen's theorem, which is what I am going to focus on. And as a corollary to this theorem, a very nice fact will come. So if you are able to prove that every prime ideal is finitely generated, then you will be able to prove that every ideal is finitely generated, meaning the ring will be Noetherian. Those who do not know this terminology, do not worry at this point. So to check, so this line is for people who know some terms like Noetherian. So to check Noetherianity, it is enough to check that every prime ideal is finitely generated. That will come out as a corollary to this. Corollary to Martin Isaac's will come out as saying that if every prime ideal is principal, then the ring is a principal ideal ring. Okay, so many of these have such corollaries, and which are very nice corollaries. Okay, so as I said, since this principle is not brought out in textbooks, it is good to know this principle. So let me begin with the proof of Cohen's theorem. Let me again show you what Cohen's theorem is, so that we are sure. And I'll give you a moment to read it. So I is an ideal, and I is not finitely generated and is maximal among all ideals in R that are not finitely generated. Then I is a prime ideal. So our aim is to prove I is a prime ideal. We will start the proof by saying, suppose I is not a prime ideal. Okay, so that is where we are starting the proof. So since I is not a prime ideal, we have elements in R such that the product is in I, but neither A and or B belongs to I. Okay, so A and B does not belong to I. Then I is contained in I, A. Why? Because A is not in I. So you have elements A, B such that A, B belongs to I, but A, B does not belong to I. You have such elements. So I is properly contained in IA. IA, ideal generated by I and A. And hence is finitely generated, because I is maximal among ideals that are not finitely generated, and you have produced an ideal that is bigger than I. So hence it is finitely generated. And say generated by these elements. I1 plus x1a dot 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 in xna. Xi's are in the ring R. Okay, my ring is commutative ring with unit. Now consider the ideal J, which is I colon A. Okay, let me explain what this I colon A means. Okay, I colon A is, so this ideal I colon A is the set of all elements of the ring such that when I multiply with A, it lands in I. Okay, so what is the definition? Let me tell you. So the ideal J is nothing but the set of all elements of the ring R such that R times A belongs to I, where R is an element of the ring. Clearly, I is strictly contained in IA. Why? Because you see, B is not in I, but B is in IA. So this is, and I is in IA. I is in IA and B is in IA too. Thus, IA is strictly larger than I and hence finitely generated by what we assumed, okay, like just before, like 0.2. Now, upshot of this has been, so far, let me tell you what the upshot is. So far, what we have done is, we have produced two ideals. One is I comma A and another is I colon A. Both finitely generated. Okay. Now, I am going to make a claim so that the proof structure is completely clear to you. So just to make the proof structure clear, I am ending it here. The 3 points, bullet points, show you that I comma A and I colon A are finitely generated. We will prove that once you have I comma A and I colon A are finitely generated, we will see that I will automatically be finitely generated. So this implies I is finitely generated, but that is a contradiction. So I is a finitely generated, will prove, and that is contradiction. Why is it a contradiction? Because I is maximal among non-finitely generated. So that is a contradiction, and hence our assumption that there are this kind of elements is false, and hence I is prime. So that is the end of the proof. At this point, maybe I don't know whether it's a good idea to ask a question. Maybe I prove the last upshot. What is written? The upshot is IA and IA are finitely generated. Then this implies I is finitely generated. Okay. So let us try to prove that fact, and maybe then I will. So I hope the structure of the proof is absolutely clear. That's why it was just made into 4 steps. Okay. Now let's go to this theorem. This should not be called a theorem. It is just some lemma. If IA, and I'm calling this an ideal J at the moment because I want to use just the notation J in the proof rather than all the time IA. So if IA and this I colon A are finitely generated, then I is finitely generated. That is left. So let's prove. Claim is, we are saying it is finitely generated, and I am directly telling you how it will is finitely generated. This I1, I2 to IN appeared here. See, then I, which is is contained in IA, and hence IA is finitely generated, and it is generated by this I1 plus X1A dot 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 IN plus XNA. So the I's that I took there are this exactly same I's, okay, coming from this proof. So I'm saying I is finitely generated, and it is in fact generated by I1 to IN and this J times that element A. That is the claim. So let's look at the claim. Let Z belongs to I. We have to show two containments. I claim that the right side is contained obviously in I, and I will show you if you do not believe me. But let's do the part which is not trivial and which requires some calculation, but it's easy. So I will show that I is contained in this ideal, and trivially this side will be contained in I, and hence we'll get that I is generated. I mean, I is this. So let an element Z be in I. More so, Z is in this ideal because I is contained here. So Z belongs to that. Since this was finitely generated by such element Ij plus Xj, we can write that Z as linear combination like that. Ri is coming from the ring. R1, I1 plus X1a plus dot 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 Rn, In plus Xna. Okay. Before going to this third step, let me tell you why this third step happens. Now Z belongs to I. Now let's look at all this R1, I1, R2, I2, Rn, In, some of those. Okay. Forget the other ones. R1, I1 of course belongs to I because I comes from I. So Ri, so summation J equal to 1 to N, Rj, Ij belongs to I. So when I pull it on the other side, Z minus that summation is in I. That means the distribute Ri's in the second factor. So R1 X1A plus R2 X2A plus dot 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 Rn Xna belongs to I. But that precisely means that this is belongs to J, and that's how I get that this element belongs to J. Okay, by looking at this identity, moving all Rj, Ij to the other side, and seeing the rest belongs to I, and hence this sum belongs to J. So I have proved that Z belongs to this. Why Z belongs to this? Because Z is what? This again expanded out. R1, I1 plus R1, X1. So this is R1, I1 plus dot 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 Rn, In plus this sum and entire times A. And that is belongs to J. So that belongs to J. And this belongs to the ideal generated by I1 to In. So Z belongs there. And that is what we wanted to prove. So let me just tell you how the right hand side is contained in the left. All the I's anyway belong to I. Now this J times A anyway belongs to I. And how is that? Okay. Now at this point, maybe it is a good idea to let me do the corollary, and once the corollary is over, maybe we discuss, because I at the moment only want to focus on this theorem, and I can say something more about other theorems also, but let me finish. Maybe that is a better idea. Why this JA etc. Belongs to I? It is by definition, basically, almost. So this is over. Let us do another theorem of Cohen. If every prime ideal in a ring is finitely generated, then R is Noetherian. Okay, R is Noetherian means every ideal of I is finitely generated. So basically, the theorem is saying if every prime ideal is finitely generated, then every ideal is finitely generated. And the strategy goes as follows. Suppose there is an ideal that is not finitely generated. Okay, and this. Then using Zorn's lemma, you can find an ideal I maximal with respect to being not finitely generated. By previous theorem, this ideal has to be prime and hence finitely generated by the hypothesis. And then you are done, because that's a contradiction. And so you say that the poset you took is empty, and hence all ideals are finitely generated, basically. So I would say it is a good idea at this point to stop and ask just questions, and then I can say a few things about other theorems. I can make a few remarks after that. So point is, all these theorems follow a same kind of, you have to do some changes here and there, but more or less the strategy is similar. But of course, everyone you have to do slight change here and there. But more or less it is similar ideas. And then finally, I want to give you the reference. So rather than keep going and proving another one, I think it is good to just show one, and it is maybe good to understand this one. Understand one theorem, and the others you can do yourself. And if need be, I can continue, not today, but some other, not as a part of some symposium, but just a few lectures on such theorems, how to prove all of these other ones also. I can give another lecture on that. But at the moment, for the benefit of everybody, I think I should stop here and let you ask me some questions. Oh, please define J again. Okay, J again. It's called colon ideal or ideal quotient. Okay. It is the set, or this is a set of all elements R/in R such that R times A /in R times A belongs to I. So this is the definition I have typed in the chat. It will be good at this point to understand this proof. I have presented, hopefully, by 3 or 4 points each, and hopefully it was clear. If it is not clear, I am ready to explain. But as I said, rather than going through all the theorems one by one, it is better, I think, if I just explain this and to understand this. All the others will follow similarly. So now it's up to you to ask me question. If you have understood everything, great. We can discuss, and then I can give you further references. But as I said, there is no point really. It is as it said, mutatis mutandis, everything follows. Meaning with appropriate change in symbols and notations, all the theorems go the same way. So it is important to understand this theorem, this one theorem, and then you can understand every one of them. For example, to prove I is maximal among non-principal ideals and prove I is prime, it goes almost the same way. Of course, with slight change. And then as a corollary, you get that if you prove every prime ideal is principal, then you can prove that the ring is a principal ideal ring. If you can prove that every invertible ideal is prime, then you can prove that every ideal in the ring is prime, R being a domain. So this kind of theorems are very common. Now, I don't know whether it was common to you or you knew about it. So let me ask one question to you guys.
From Bharati Vini, what does maximal with respect to some property mean?
No, maximal with respect to meaning under inclusion, maximal. So for example, suppose consider the set I. Suppose I consider the set following set I. I is an ideal that is not finitely generated. Then somehow using Zorn's lemma, I will prove that this S has maximal element. So with respect to inclusion, so we are forming a poset, and then within the proof, nobody asked me that question yet in the proof, but for example, nobody asked me, there is something that you have to do at this point. Suppose there is an ideal that is not finitely generated. Then using Zorn's lemma, you can find an ideal I maximal with respect to being not finitely generated. Of course, to use Zorn's lemma, you should have a non-empty poset and show that every chain has a, so if P is your poset, partially ordered set, non-empty, and you take a chain, then every chain has a maximal element in P. If you can show that, then by Zorn's lemma, there is a maximal element. So maximal in that, you are ordering the poset with respect to inclusion. So maximality hopefully is clear. I would rather want to discuss if you understood, because it should be that you. I mean, I really would like if you understood the proof. It's not about me presenting several proofs. I can present because, as I said, I can present some of them. I had done as exercises, so I have it written. So I can just present all of this. But the point is, it might be better to actually see. So what I would say is the following, that this is still not totally clear, okay? Meaning, then using Zorn's lemma, you can find an ideal maximal with respect to maximal with respect to being not finitely generated. So what you have to do is following. The union of a totally ordered chain of ideals that are not finitely generated is not finitely generated is what you have to prove. It's easy to prove. Suppose I is the union of I alpha. Suppose I were generated by A1 to AM. Then this A1 to AM will belong to some I alpha. And then, of course, I alpha will be generated by this A1 to AM. Because I was generated by A1 to AM. But that contradicts the fact that I alpha are not finitely generated. And that is how you will use Zorn's lemma. So that one point I have left, mainly to not cloud the proof, the structure of the proof, because I wanted to keep it into 2 steps and 4 steps earlier. In earlier, the only step maybe that is not clear is I have not, again purposely not put one more bullet point explaining this 3rd bullet point. I hope that is clear to you, otherwise you should ask. It's been presented in a few bullet points precisely so that it is easy to remember the proof rather than write a lot, because sometimes writing a lot during a presentation you lose the structure or the idea, and I didn't want you to lose it. At least that happens to me. So any questions, or is everything clear? If everything is clear, can we do, rather than me presenting, I would like you to tell me how we can see, because it's about, again, I hope the idea is not just about, some presentation. Ideally, we want to learn something from each presentation. So if we want to attempt together, all of us together, attempt Martin Isaac's theorem, that if R is a commutative ring such that all prime ideals are principal, then R is a principal ideal ring. If you want to attempt that, then we can do it.
Don't we need to show that we have a bounded chain for using Zorn's lemma?
Yeah, so that's what I'm saying. That is what I repeated the proof. Suppose you have a union of a totally ordered chain of ideals that are not finitely generated, then you have to show it is not finitely generated. Then this thing will lie in T itself. So every chain has an upper bound you will show as you require in Zorn's lemma, and then using Zorn's lemma you will say that there exists a maximal element. So you have to make that proof step here, which I repeated actually. So take the union of a totally ordered chain I alpha of ideals that are not finitely generated, call it I. So I is the union of I alphas, and you want to show that I is not finitely generated. But that is easy, because you will say that suppose I were to be finitely generated by A1 to AM, then since I is the union of I alphas, this A1 to AM will belong to some I alpha. And as a consequence, this I alpha will be generated by this A1 to AM. And hence I alpha will become finitely generated. But you started with the union of not finitely generated. And that's how you will.
And we are done.
Yeah. If you're not asking me any questions, let me at least show the reference. Okay, so now you see the reference. Now let me answer Mithun PV's question. Does this follow for every maximal property? Well, every maximal, I would say, will not follow. You see, I cannot just say that everything, but you can characterize. And this characterization is given exactly in this paper. that I have mentioned at the end as a reference. Here is the paper. T.Y. Lam, M.L. Reyes. T.Y. Lam has several books. It's like almost like Lang. He has 4 or 5 books. Lang has many. But T.Y. Lam has a lot of books written. And he is a professor at Berkeley. I think I now retired. And they had written this in 2008. And I had considered this problem, unfortunately, 3 years late. Because I was looking at that time thinking that because I had proved some of these theorems, at least 5 of those theorems at different times I had proved. And in TIFR, I was proving 2 of these theorems as exercise from a book. And I thought, oh my God, I have proved something like this before also, and almost similar it goes. And at that time, I didn't remember the proof. So I went and looked back into my notes, and the proof almost all went similar. That's when I decided maybe I will write a paper saying that all this can be maybe done under one umbrella. But while searching for more such things, I already ran into this paper. They had already done. In fact, M.L. Reyes, the student, has several other papers, at least 2 more, written on prime ideal principle in 2-sided ideals, a prime ideal kind of principle in a non-commutative setup. No, so it says a generalization of theorems of Kaplansky and Cohen or Kaplansky and Herstein to non-commutative rings, etc. So you can look up Reyes' papers. He is writing on this prime ideal principle. And I could have done this itself actually. So since I had seen that paper, a few years ago, I had guided a master thesis, and I had asked the person, the student at IISER Thiruvananthapuram, to read 2 papers in commutative algebra. One is this, and another is another about 70-page paper, which gives some good information. And one of them was this. So I could have presented that way, meaning the way they are writing this. So it is in a very general setup. It starts with something called Oka family and Ako family. Oka means OKA, and the reverse is Ako. So they start with the definition of that. It is just very simple. But then if I present it that way, the first 20 minutes will just go on that new language, Oka family, Ako family, etc., etc. And then maybe you will lose interest, and then the main beauty or the theorems that I wanted to present would be lost. And hence I didn't go that route. I just went very directly into the proof and said that there is a principle like that. So the principle appears in this paper, and I think you should read it if you have time. Only problem with the paper is that the first 2-3 pages itself will bore you, because it starts with, say, this general setup. That is why I didn't present it that way. But this was done by one of my students 2-3 years ago as one of the papers that they read during their master thesis. Now it is up to you to discover more, and if you do, please do let me know, because at some point, as I said, I have already proved at different points. I have in my book proof of 5 of this. The last property that I showed, I did not know, and I only learned from this paper, and that is this property theorem. I will show you back. I will show you all the theorems. It's this last one. An ideal maximal with respect to containing only 0 divisors is a prime ideal. This I had done as an exercise. An ideal maximal non-invertible, not countably generated, not non-principal. This all I had done as exercises. 2 of them, maybe you also have done it. So now it is up to you to discover more, and I hope this was beneficial. I'm sorry that I didn't take full time, but as I said, it was on purpose, highly purposeful that I just did this much, because I wanted to leave room for a lot of time for you to ask questions, rather than just me presenting several of the proofs of this theorem, because it all follows the same way, as I said. But I would still encourage you to look at this paper and maybe rewrite it, not in that Ako-Oka family terminology, maybe in some better way. So any questions? Yeah.
So thanks for the presentation entirely, and I guess at least the audience will be able to take home the essence of the theorems, and they can look back at it and try them out at some point of time.
Exactly. That's correct. So essence, let me say one more line and then I will quit. The essence is the following. If you are coming across in commutative ring with unit, a property, an ideal maximal with respect to some property, it is not a bad idea to think that it might be a prime ideal. Of course, you need to prove it, but at least you will be able to assume maybe it is a prime, or at least you will get a at least there is some intuition you will have saying that, oh, maybe it is prime, and you might at least attempt it. So that is what I want you to take home from this talk, and nothing much. Other things you can prove it. If you are not able to prove it, ask me and I can provide you the proof.
So if some of us would like they can unmute and thank the speaker.
Thanks.
So this session will be over now. I would like to mention that the next talk for this afternoon session will be at 4. It will be given by Professor Kalyan Chakrabarti from KSOM. It is mainly aimed for beginners. So I hope a lot more people, if you have more friends, they could also join and they will really enjoy it. Thank you for this talk, Dr. Viji. And we can proceed now. We can break the meeting for now and we'll join again at 4 for the next talk and the last talk for the day.
Thanks.